This week we will see about permanent magnet machines and how permanent magnets works when it is placed in any core or any rotors. Okay, so let us start by an example. Uh, this is kind of device we made. Here, magnet is placed here. Its medium direction of the cat magnetized along its length, which is L. Okay, number of transfer stages, TPA. And here this is the air gap, which length is LG. And this magnet is a neodymium magnet, right? And I hope you might have studied about magnets. We earlier also discussed about magnets. There are, of course, type of magnets which are popular, which are generally used in electrical machines. So neodymium magnet is the major magnet which is used in almost many instruments, and the reason behind is it has very high energy compared to other magnet components. Now, it's the remnant flux density of neodymium. Br of neodymium is 1.2 Tesla. PM coercivity, PM coercivity is 860 kiloampere per meter. And it is to be considered that the magnetization line is a straight line. Okay. What PM coercivity and BR means here, so basically we have a second quadrant operation and we have to assume a straight line demagnetization. So it will be 1.2 Tesla and this coercivity is 860 ampere turn. Okay. This is at load and this will be intrinsic characteristic. Now, air gap length is provided at 0.5 mm.
Sir, sorry to interrupt you. Actually, voice is not that much clear. There is a some breaks are coming in between.
Oh, okay. Sorry about that. Let me skip my internet connection. Is it because of internet, or do you think it is it because of
It
my
is because of
microphone?
internet only, sir. I think
Internet only.
internet only. It's breaking in middle actually. Voice is breaking in middle.
Okay, okay. Let me see. Am I audible now?
Yeah, I can hear you, sir.
Is it better than earlier?
I think just we'll wait for 1 minute. I think then I decide.
Okay, okay, sure, sure.
Now it's
I'll
fine.
carry on. Okay, okay, great. Yeah. Mm, Okay, so I hope till now what I was saying that this permanent magnet is placed in an electromechanical device which core consists an air gap as well as it has a neodymium magnet with its Dr and Hc is given. Right now, PM thickness also it is mentioned at 12 mm and leakage factor.
Okay.
Yeah, is it fine now?
Oh yeah,
Leakage
it's
factor.
yeah, yeah, yes, fine.
Okay, thanks. Leakage factor is 1.25.
Okay.
And one important information is given that magnet area is equal to air gap area. And this PTH is also provided as follows. We have to calculate relative permeability of the magnet mu r.
Mm. Hello?
Yeah,
Yeah. Yeah. Sir, we can use the formula na, B equal to mu naught into mu r into H relation.
exactly, exactly. We are given with Br, okay,
Yes.
and we are given with H. We know
Yeah.
mu naught, mu r we can calculate.
Yeah.
Right? Yeah. So we need mu r. Br is 1.2. Unit is 4 5 into 25 minus 7. Let's say it's 16 kilo. It's 0.4. So from here, which whatever value will come, that will be the value of mu.
Mu r value.
So
Okay, C value 860. One 1.11.
1.11 exactly.
Oh, yes.
So its mu value is 1.11, and if you observe carefully, you would get to know that this value is very close to relative permeability value of the air. So
Mm.
generally, relative permeability of magnet is or magnet path in the reluctance circuit is considered as air, along with MMF source, but reluctance is considered as air only. Okay.
Okay, sir.
Now the second part of this problem is how to calculate no load operator reluctance. So to calculate no load operating flux density, do you have any expression derived?
No, sir. Not sorry.
Okay, okay. Let me write it here. So the expression you can go back and also see that B naught is equal to VR divided by 1 plus mu R into LG by AU into AM by LM into 1 by K. Okay. So with this expression, you will get no load operating flux density. Why? Because in this expression, you can see that air gap and magnet has only the higher reluctance part. That's why we are considering MMF along the core as negligible. And if you equate both the equations, you will get the parameters of air gap length, area of air gap, magnet length, as well as area of magnet. Okay. So basically, this denominator will be higher than 1, right? Why? Because the energy of magnet, let's suppose ki our core is uh, permeable enough, so it won't consume much energy, but air gap, it will draw much flux, right? And to draw much flux, its operating point, let's suppose if our core is infinitely permeable, the operating point is this. Now, if we have introduced some air gap, it will move towards certain load line or certain load, right? And this considered as load line of the magnet if the magnet is operating at this point. And at this point, with respect to air gap, as air gap increases, right, this operating point moves towards the its coercive force, right? Because more coercive force will be required. And our no load operating flux density will further reduce and reduce. So that is why I mentioned that this value is larger than, right? Now, if I plug in all those values, 1 plus mu r is given, or mu r that we just calculated, 1.11. LG air gap length is given 0.5, LM is given 12 mm, and area of magnet and air gap we have to consider it as 1, and leakage factor is 1.25. If you calculate this value, you will get the value of no load operating flux density.
1.157?
1.157. Yes. Yeah. Yeah, it seems to be correct because first thing is to verify that it is less than BR. So yeah, it is correct value. Any doubt
Sir,
regarding the, yeah,
sir, could you give me the gist of this problem? I have joined little late, so could you give
okay.
me a gist of this problem?
This B part or A part as well?
Yes, sir. Both.
Okay, okay. So see, the problem consists an electromagnetic device, right, where a permanent magnet is placed here. This is permanent magnet with such length, BR, positivity, everything is provided, right? Leakage factor is also provided. And also mentioned that magnet area is equal to air gap area. Now, there is air gap in the circuit. So what happens? A flux will be established in the air gap by permanent magnet, right? And because of the, this magnetic circuit, its operating point of magnet will shift from this dominant flux density point to with respect to how much coercive force is being applied there, right? So how much will be coercive force of this air gap?
Eight 60.
Uh, Not exactly. Like how much? What is the H? V by me. Right? So
Yes, sir.
how much flux is being established in the air gap, right? Accordingly, that much this coercive force will be applied there, and that much coercive force will be supplied by, or that much coercive force operating point is being supplied by permanent magnet, and that is why this operating point is being shifted from 1.2 Tesla or BR or remnant flux density to some operating point flux density, even at no load. Right? At full load, the story will be further interesting, but even at no load, this shift in operating flux density of permanent magnet is happening. Right now, first part was very straightforward. We had to calculate relative permeability of magnet, and relative permeability is nothing but from this equation we can easily calculate, right? Br is equal to mu naught mu or SC. Mu naught we know SC is given the problem. Br is also given at in the problem, so we easily calculate this value of mu naught. I hope A part is clear to you.
Yes, sir. Sir, what is that corrosivity?
What is the coercivity? Yeah, see, if you might have gone through the lecture, this is BH curve second. And permanent magnets, like there are four permanent magnets. So here we are talking about NdFeB, neodymium. All the permanent magnets, does how do they operate? They create flux lines, right? They create flux around the core or a magnetic path. What happens when they are creating flux, right? Like here, we are ignoring, you know, what to say, reluctance of the core, because the major part of the flux is, or major part of energy of permanent magnet is going into establishing the flux in the air gap, right? And when that happens, it means permanent magnet is supplying, it means it is operating at certain coercive force, right? So, how to further simplify it? Let me, okay. Yeah, other simple way is to observe is like this. V is directly proportional to H, isn't it? Now, how H will increase?
Sir, what is your question?
I am asking, uh, V is directly proportional to H, right? V
Yes,
is equal
sir.
to mu into H. Okay.
Mu into H. Yes, sir.
H means indirectly we can understand H as loading, right? And loading loading means how much energy we require at the load side. That will be supplied from the source, and source being permanent magnet here, isn't it?
Yes, sir.
Yeah. So as this loading will increase, okay, this B will further, because how is it varying on in the second quadrant? This is the characteristics of magnet. This is not derived from anywhere. This is just the characteristics of magnet. As H will increase, this B will shift. B will vary according to H, isn't it?
Yes, sir.
Yeah. So as higher the value of H, as higher the loading in the circuit, in the magnetic circuit, your magnetic flux density is going to reduce or increase.
It will decrease, right, sir?
It will reduce, exactly. So as load will increase, your magnetic flux density of permanent magnet will reduce. Okay. So this was very crude way to explain. And here I have written B directly proportional to H, but according to this slope, you could derive the expression between them. And I think this expression is derived with this formula here. So this is the expression which is derived from that load line, that at any operating point, here we are being asked about no load operating point flux density. So even at no load, this permanent magnet, which is placed here, it has to supply to that load. And what is the load here? Can you let me know what is the load here in this electromechanical device?
That permanent magnet is the load, right, sir?
A permanent magnet is source here,
Okay.
and permanent magnet has to supply the flux. And where is it going? Majority of the permanent magnet energy, where is it going? In the core or in
It's
the air
going
gap?
through the core.
Yes, and air gap, right?
Through the
Yes.
air gap, the reluctance will be more, right, sir?
Exactly. So when the reluctance is more, it means it will draw more energy to establish the flux in the air gap, isn't it?
Yes, sir.
Yeah. So that's why now this B will shift from this point. So B will now shift from this point to this point. Okay. Uh, so this is the demagnetization line of the neodymium magnet here, right? Now, because of air gap, to supply the
Yes, sir.
energy or to establish the flux in the air gap, our this B value has been shifted from this BR value to, let's suppose, this value. Okay, this value actually we calculated here, which came out to be 1.15 Tesla, but I'll explain you why is it coming. Now, you tell me one more question. If I eliminate the air gap from this circuit, okay, then this operating point will shift in which direction? Like, will it exist here, this point one, I am following it, or will it shift to here, point two, if I remove the air gap?
I think it is point one, sir.
Point one. Excellent. Why? Because now we have less load. Like only core it has to cater. The permanent magnet has to establish flux in the core only. So that is not much of what to say in terms of loading, and that's why this B will move slightly on its load line or demagnetization line. right? So I hope you got the idea how this V varies with the load.
Yes, sir.
Yeah. So that expression was derived in the lecture. Okay, you could refer the lectures. This expression is V naught is equal to VR divided by 1 plus mu R LG by LM AM by AG into 1 by Q. And in the problem, it was mentioned that magnet area we have to consider equal to the air gap area. Okay, so AN by AG we can cancel out here. So we have only VR divided by 1 plus mu or LG by LM into 1 by K. And we plugged in all those values and we got the value of 1.157 Tesla. And you could see that this value is less than 1.2 Tesla, which is the remnant fluctuance. Now you got the concept behind it.
Yes, sir.
Okay, great. So let's move on to the second part, third part actually. What will be the amount of MMF and field strength HE when current is equal to 4 ampere? Where current will be applied? Here, in this winding. In this winding, we are providing 4 ampere current. Now, what will be the excitation MMF and what will be the external field strength? I hope you got the question.
Yes, sir. MMF NI?
MMF and field strength. So MMF is equal to,
NI, number of turns into current. I.
yeah, it is very straightforward. So
Yes.
number of turns was given as 1000
1,000. Yes, sir. Turns per phase 1,000.
and current is 4 ampere. So it will be 4000 ampere.
4,000.
Okay. Now the next thing is field strength. How much will be external field strength? Basically, this field
Um,
strength will be, yeah, you have the answer. Rajni?
no, I thought that integral of HDL equal to NI.
Exactly, exactly. That's the way. Yeah. So H dot dl actually let us calculate it here. H into L is equal
Equal
to
to
L.
NI. Yes.
Yeah. So this L will be which length? Air gap length or magnet length?
That portion length. Length of the magnet.
Magnet length, exactly. So this Lm will be magnet length, and this external field strength we can calculate. So I hope you are getting why we have to use magnet length, because that much we are applying certain current here. So as earlier I explained in terms of loading, that if you apply, because H is proportional to I, okay, and if we are providing some current, this B is going to deplete, this flux density value will change, and that's why it will depend on the magnet length, because the relationship between coil, the interaction will happen where? Between the uh, coil and magnet field. So coil is establishing its field, which we are calling as external field, and magnet has its own field. Now both of them will interact as happens in any electromechanical devices, and then force generates. Okay. So here H into Lm is equal to Ni. We need to calculate H here. Ni we have already calculated. 4000 divided by Lm is 12 mm. Okay. H will be 23.
3,33,333.
Okay, yeah, exactly. It's 3,33,333.
3,333
ampere per meter.
per meter.
Sir, it is 33, not 0.
Just a second, I lost. This time. Could you please repeat? What is it?
At the last, it is 3 and not 0.
Okay.
3. Okay.
At last, still it is 3. You are
3.
saying.
Yes.
Okay.
Yes, sir.
So we can also say 333 kiloampere per meter.
And 0.33 into 10 power 6 ampere per meter.
Yeah.
33 into 10 power 6 ampere per meter.
So this much force is being applied from the external field, right? And this is huge, like this much kiloampere per meter is huge, and it will shift this operating flux density further. So now you let me know. Earlier with air gap, it was operating at point number what let us call 3. Now with this field applied, external field applied, where will it operate? At 1 or 2? Or further, let me 4. 2. Let me clarify once more. 1 was when no air gap was present. Okay. 3 was when air gap was included, right? And 2 will be when force is this external field is applied. Let me remove this. Okay. So I hope you got my question. 3 was with only air gap at no load. 2 is when external field is applied. 1 was when no air gap was present in the circuit. So when we applied this external field, the operating point will shift from 3 to where? 1 or 2?
2.
2, exactly.
2, sir.
2. It will be 2. So that's the idea behind it. As you increase the external field, as you increase the loading, your magnetic flux density of permanent magnet will further reduce because it is proportional to coercive force, which is H, which is dependent on current as well as reluctance of the machine. Okay. Any question in this part?
No, sir.
Okay, great. So let's move to the next question. Okay, now we will talk about PM motor. In PM motor, a phase winding there will be phase windings, right? If it is 3 phase, there will be 3 phase winding. So phase winding has mean turn length equal to 192 mm, and each conductor is wound with 2 strands. Okay.
Sir,
Yeah.
what do you mean by strands here?
Okay. So see, You make a wire, right? We have any copper wire. If you see it as a whole wire, right? But if you peel it, you will see inside there are multiple layers of thinner wires that are making a whole thicker wire.
Yes, sir.
Yeah, so those are called this thinner multiple segments. They are called as strands. And this one wire, entire wire, which is made up of all the strands, we call them conductor. So here,
Okay,
what
sir.
is happening that with two strands, it is making one conductor. Okay.
Yes, sir.
Yeah.
Understood, sir.
Yeah. So yeah. Now number of turns in series per phase is equal to 48, and number of parallel paths is equal to 2.
Alpha.
So in the permanent magnet motor, we can have a number of parallel paths. We can have number of turns we could design accordingly. So here, what we need to calculate phase resistance at 20 degrees centigrade, and resistivity is given. Rho of copper is given at 1.724 into 10 to the power minus 8 ohm meter, and wire diameter is given as 1.4 mm.
4 mm. So diameter. Okay. Okay. Fine. Sir.
So can we calculate this phase resistance from here?
Hmm. Rho R equal to rho L by A.
Yeah, R is equal to rho L by 8.
Sir, here L means actually mean turn length, what we used to take.
Turn, yeah,
Yes.
mean turn length of the
Here
phase.
they given like a strands they mentioned whether it is no need to consider, no, sir. It's required that data also strands.
No, no, exactly. That's why I stopped. So we have to consider number of strands also we have to consider, and we have to consider parallel paths. We have to consider number of turns per phase as well, because we are being asked phase resistance, not wire resistance.
Okay, so parallel path means after R1 R2 by R1 plus R2 R1 R2 by R1 plus R2. That's what also we have to do, sir. Means like if it is parallel, the resultant
Exactly.
distance.
That's why the number of parallel paths come in the denominator.
Okay.
The whole number of parallel paths, like if you will design a motor, you also have to, take care of number of parallel paths, because if
Parallel
you
path.
want less losses, or if you want, less voltage and more current, then you might have to increase the number of parallel paths. So that's one thing. Now, number of strands. Multiple wires are consisting to one single wire. It means indirectly they are in parallel. We can consider them in parallel, and that's why this number of strands will come in denominator as well. The more number of strands, your phase resistance will be lesser.
Yes.
Right? So
Yes, sir.
that's why we try to incorporate as high as number of strands. Now, other thing is turns per square, where will it go? Numerator or denominator?
And numerator only, sir.
Numerator, sir.
No, numerator, exactly. Because the more number of turns, more resistance will
More
be there, isn't
resistance
it?
is there. Yes, sir.
How our resistance expression is wholesome. Now we can calculate.
Sir, what is the need of turns per phase here? Because already phase winding mean turn length we already know.
Exactly.
Total phase
We,
winding mean turn. Mean turn length here means one turn or what exactly mean turn length? Okay,
yeah,
one
see,
turn
mean,
length, sir.
yeah, like how do you calculate mean term? Like one term is getting
One turn
completed,
length.
right?
Here 192 in the sense one turn length or 48 turns length.
No, one term length. One
One
term
turn
length.
length is 192, so here 48.
Yes.
Okay, sir. Got it.
Area we have to calculate. Area will be
Height is square by 4 and d diameter is given 4. Yes, sir.
exactly two parallel paths, two strands.
Number of turns 48.
Sir,
Yeah,
for area, can I use pi r square?
yeah, we are using that only. Pi d square by 4 means r. Yeah, go ahead, please.
That's what, sir. I used pi r square. Is that okay? Or will the
Yeah,
values change?
that is okay. You just have to consider it into r. 1.4 mm diameter, you have to divide it by 2 to make it radius, and then you can use as pi r square.
Okay, sir.
Okay. This 4 and 4 will be cancelled. After calculation, please let me know the value.
Sir, 6.45
6.45 ohm. Ohm, you
milli.
are saying? Milliohm. value does not seem to be correct, but
Okay.
again, it is only calculation, so you could verify on it. Mm,
I'm also getting the same answer, sir.
Acha, see, here one mistake I have done. I have viewed L as 148 and also number of terms as
Ah,
48.
48, yes.
Yes.
Yeah,
Yeah,
that's why you
148.
might
I
be sorry,
I
sorry for
noted
my
it actually, but I thought I was wrong. Okay.
no, no, no,
192.
no. And one more 10 raised to power minus 3 because 192 is mm, right? So that's why one more 10 raised to power minus 3 we have to. And actually, if you see the assignment problem, I think 6.45 million was in the option. So it was designed very carefully.
Yes.
So it should come out today.
25.
2.58 into 10 power minus 7.
2.58 to 10 raised to power minus 7. Um, that's a lot of 10 raised to power minus. I guess if everything is correct, you should get in terms of milliohm. Your value is correct. You might have increased the number this unit or terms, or it is also possible that this unit is wrong, but it's what was mentioned in the options. So anyway, this is a calculation, so you can do it. Okay.
Yes, sir.
Correct, sir. 25.8 milliohm, correct, sir.
Okay. Okay.
That
Okay.
much
So
one.
do you just verify on your own and
I'm getting 0.0258 actually. So if you convert into ohms to milliohm, then it must be 25.8 milliohm.
exactly. Okay.
Okay, sir. I'll just verify it once.
Yeah. Okay. After this problem, there are two theoretical problems. Uh, one is related to Hall effect sensor, and so first let us see what is the work of Hall effect sensor. There are four options: that it generates power, it
Mm-hmm.
controls torque, it measures rotor position, or it provides thermal protection.
Measure the rotor position, sir.
Exactly. Hall sensor is used to detect rotor position. Mostly almost all brushless motors, they have this Hall sensor or position sensor, but generally Hall sensors are preferred because of its current sensing capability, right? So Hall sensor is used in measuring of the rotor position. Okay. Uh, Now the fourth question is related to, compared to brushed DC motor, brushless permanent magnet brushless motor with sinusoidal excitation. What does it offer? Okay, brushless PM motor is better compared to a brushed C motor. In which term it is more advantageous? options are higher torque at low speed, reduced clogging torque, lower efficiency due to complexity in control, D, all of the above. So we have to identify in which area our brushless permanent magnet motor offers advantage compared to the conventional brush DC motor. What do you think?
Higher torques are at lower speeds and reduced clogging torque. These two things only.
But we have only one option to choose. And why do you say a higher torque at lower speed? The reason, and also the reason behind clogging torque.
Mm, Higher torque at lower speeds, it is started at the time torque is more actually. At even lower speeds also, there is a constant reason is there, no?
Constant torque reason.
Constant torque region, flux weakening also is there. So I feel like first one is okay. Higher torque at
So
lower.
if nothing is mentioned, then we can assume that magnetic loading as well as electric loading is equal in both the machines. Okay.
Oh.
And if we keep magnetic and electric loading equal, it means torque will be equal in both the machines. We have to consider. And so that's why we cannot comment on torque, because if somehow you have established the flux density equal to permanent magnet machine and you are supplying similar current, so other than that, I don't think any other reason for higher torque at low speed, because DC motor also can offer higher torque at low speed. Even DC series motor is known for that only. And in fact, this series motor has so much higher torque capability that we do not even start at unloading or at load. So that option we have to discard. What about lower clogging torque?
Clogging torque.
How is it lower compared to the conventional brush DC machine? Basically, in brushed motor, what happens? Commutation happens. So every
Electron.
time, yeah. So due to electronic commutation, every time this torque curve will go like this. If you see, if you might be aware about switch reluctance motor characteristics, so or BLDC in fact. So at time of commutation, it goes like, isn't it? And it is what is causing torque, because at every switching you have a dip there.
Okay.
Okay. But on the other hand, with sinusoidal, this is why is it happening in BLDC even? I am talking about even BLDC, because that characteristics will be more similar to DC motor, because we have commutation at every 120 degrees. We are switching our current, we are giving current and making it zero. Now the next phase will start operating from here. Like
120. Yes.
yeah, 120 degrees. So
120.
this dip, because of this dip or this absence of or during commutation period when one phase is going to turn off and another phase will come in action, that in between period will create a dip in the value of torque. And that is why more clogging is there or more torque ripple you can say because of that. But what happens with sinusoidal excitation? Actually, the term could have been, torque ripple should have been better. Clogging torque, it also happens at no load. If you rotate the permanent magnet rotor at no load, there is also clogging torque. However, at load also we have to overcome that force. So that's why clogging torque is undesirable in any machine. But yeah, so that's the reason behind any brushed motor, because due to commutation we will not have uniform this kind of torque profile. But what happens when we provide sinusoidal supply like this? All the three phases are active there. Okay. So there will not be any standard when one phase is going out and another phase is coming out. Simultaneously, very smooth RMF will be generated in the machine. So if you see cut profile, it is very smooth compared to the brushless BLDC operation, which we also call it as a square wave operation or trapezoidal excitation, you can say, right? So trapezoidal excitation has major issue related to cognitive torque harmonics in the machine. So that's why we prefer sinusoidal excitation. To eliminate harmonics, yeah, torque ripple very less compared to trapezoidal excitation, right? So if you let's suppose you have purchased a motor, okay, you have two options. This trapezoidal excitation, generally it is called as BLDC, and sinusoidal excitation, which is called as PMSM. Okay. Now, if you see the structure of core, rotor, stator, permanent magnet, okay, it will look alike. Both of the motors will be identical to each other. Only, thoughtful combination may change. That will again depend on how you have designed. You could also keep both of them same. Then you have two options. To run both of these motors, you will require controllers. Controllers are also available in the market. You will have two options: trapezoidal excitation and the sinusoidal excitation. So uh, you are asked, and both of them have their objective. This trapezoidal excitation claim to provide 15% more torque. So same law. Okay. And I think it is mentioned in the book by Ramu Krishnan. You could prefer that. So uh, you are getting 15% more torque in trapezoidal excitation, but on the other hand, in sinusoidal excitation, your harmonics are getting reduced, your torque ripple are getting reduced. So it's completely depend on you that whichever excitation, whichever controller you are going to choose, right? So there is not a single answer to this problem that which excitation, which controller you should choose. But generally in industry, the trend has been seen that for low power, for less than 1.5 kilowatt, This trapezoidal excitation is preferred, and for higher power, because when higher power comes in the picture, we cannot afford so much harmonics and torque itself. Right. And even at higher speed, it becomes more and more critical to reduce rolling torque itself. And also, it may happen that at higher power, your harmonics in trapezoidal excitation way more than whatever is required to maintain the rated value of torque. So in some cases, because of harmonics, your sinusoidal excitation based motor may produce higher torque compared to BLDC or trapezoidal based motor. Okay, I hope this is not very much complicated, but again, you have to be in a continuous touch with all those news and all those topics. So you could look in internet also. I hope it is not much confusing, but still, if you have any question, please ask. Okay, so if no questions are there, then the next question is, which slot pole combination is most efficient to use from a perspective of lowest inverter switching loss for a BLDC motor? Its rated speed is 3000 RPM. Options are 9 by 8, is 15 by 14, C is 6 by 4, D is 15 by 16. It is written in terms of not per pole. So what do you think? Which slot pole combination will be most efficient?
9-8?
9-8. Why do you say so?
Uh,
Reason behind 9 by 8 is
slot pole ratio, one important. Second one is a 3000 RPM, no rated speed,
hmm,
not much higher.
okay. But here the constraint is only efficient.
15 is
So
constraint.
yeah, like we have to choose a slot pole combination based on the lowest switching loss.
Huh.
And this lowest switching loss will be dependent on how much our losses is happening in the,
Mode slots.
yeah. So like uh, first calculate the frequency of the motor. N by 1.2. The highest frequency will be in highest number of poles. So basically frequency is dependent on the number of poles.
Yes.
So the lesser the number of poles, lesser will be operating frequency of the machine.
Mm.
Right. And because of that, lower iron loss component will also be there in BLDC motor. But again, this if this frequency is less, then switching frequency will also be less, isn't it? Because
Mm.
switching frequency is generally some factor of our machine frequency. So if your motor frequency is less, switching frequency would be lower. And if switching frequency is lower, your inverter switching losses will also be low. Okay, so that's why we have to go ahead with a lowest number of poles. Okay. Even to minimize losses in the machine, we should go ahead with the lowest number, right? All the frequency dependent losses are directly proportional to the frequency of the machine, and which lead to higher inverter frequency, and that will further increase the switching losses. Okay, so that's why lower the number of poles are better, but again we have to also take care of many factors. So that's why we cannot straight away go ahead with lowest number of poles. But for this particular problem, the options will be correct. Okay, any doubt?
Understood, sir.
Okay, great. Hmm. Yeah, other question is also theoretical. What is the BR of ceramic family magnet? Ceramic family means ferrite magnet. What is the BR range?
It's 0.41 to 0.43 Tesla, sir.
Yeah, yeah. Generally, it's 0.41 for all the lattice ferrite magnets, but in the options you were provided between 1,000 to 4,000 Tesla, and all like it was the A option, B option was 8,000 to 11,600 milli Tesla, milli Tesla. So we can choose because 0.41 and 0.43 Tesla, 0.45 Tesla, these are all maximum value. But lower energy of ferrites are also available in market. And some are also called as bonded ferrites, which have way lower value, like 0.2 Tesla, 0.15 Tesla. Okay. So generally, it is considered from 1,000 to, you can say 4,500 milli Tesla, but suitable option should be 1,000 to 4,000. Okay. So whatever you mentioned,
Sir, how it
0.41
is
Tesla.
possible, sir? 4,000 milli Tesla in the sense 4 Tesla, no?
Ah, okay. Yeah, yeah, yeah. Sorry, 400 it should be. Exactly, exactly. Thanks for pointing it out. I think current week assignment also it is there. So you just take care of it. It is typo, I guess. Okay. So
Even in the assignment also they did same things, sir.
yeah,
Option
yeah,
A is 1,000
they
to
have
4,000 milli Tesla.
they have repeated, but again you have to either you raise the question or
Have to write a question to them.
yeah, and also one option is none of the above. So appropriate would be none of the above, but you can raise a question there.
Can I write none of the above, sir, over there? Otherwise, I have to select first option and I have to write a question to them that, okay, this please verify. Like,
From their side, they have considered 1,000 to 4,000 millitesla as correct. But
uh,
if you can argue with them, I think they can modify to none of the above, or they can modify.
they can modify the answer.
Anyway, so let's move on to the next problem. A permanent magnet in SPM. So SPM means surface mounted permanent magnet.
Okay, surface permanent magnet.
Yeah, surface mounted PM motor. In surface mounted PM motor, magnets are glued at the surface of the rotor. Okay. So whole face area is 625 mm square and length is 7 mm. dr is 1.1 Tesla. Required permeability is 1.05 of the permanent magnet.
Okay.
Air gap area is 700 mm square. Effective air gap length 0.7 mm. Leakage coefficient is 0.9. Now we have to calculate internal magnet permeance. And for this, you will have to look into the expression of permeance, right? And if you even know the expression of reluctance, you could also get to know the expression of permeance, because permeance is nothing but inverse of reluctance.
Reluctance.
And permeance is equal to L by mu naught mu r a
By
divided by L.
yeah.
I think we are given with all the data. PM area, is not given. All given. Six, yeah, pole face area. Length is also given. So can we calculate the internal magnet for me? Please calculate. Excuse me for a couple of minutes. Yeah, so I hope you have calculated the value of permeance.
Yes, sir. 1.17 into 10 power minus 7 Weber per ampere.
Into 10 power minus 7 Weber per ampere. So it is the correct value. If you plug in all those values, you will get the value. Chittu, are you getting the same value?
No, sir.
Uh,
I got little confused. Could you
okay.
explain me?
Yeah. So see, this permeance value is mu naught mu r A. You know the value of mu naught. How much is it? 4 pi into 10 to the power minus 7. Mu r value is given, right?
1.05.
Into 10 power minus 7.
Mu r value is 1.05. Okay. Mu naught is 4 pi into 10 to the power minus 7. Mu r is 1.05. Area of magnet are you given with?
625 into 10 power minus 3 whole square.
Yeah. So see here in the problem, pole face area was given, and in surface mounted motor, the pole face area is nothing but your permanent magnet area. Okay. So that's why this magnet area you have to consider as 625 mm square. Okay. And this length is also mentioned with
Yes, sir.
7 mm. So this length you can plug in here. I hope now you will get this value.
Yes, sir.
Okay. Any doubt?
Understood, sir.
Okay, great. Now let me know the value of air gap reluctance then. Part B is air gap reluctance. How will you calculate air gap reluctance with this much data? Air gap length and air gap area, if you are given, you can easily calculate air gap reluctance, isn't it?
Yes.
Air gap area, I can see here, 700 mm square. Air gap, effective air gap length is mentioned 0.7 mm. So let us calculate the air gap reluctance. L by mu naught into AZ. AZ and effective air gap length is given, including Carter's coefficient. So 0.7 mm divided by 4 pi into 10 to the power minus 7. Area of air gap is 700 mm square. What should be the value of this reluctance? Please calculate.
Seven lakh 95,774 is coming.
95, 7.8. Ampere per
795.774 into 10 power 3 ampere for Weber.
Okay, that's correct. Chitu, are you also getting the same value?
Yes, sir.
Okay, great. So now we have calculated air gap reluctance as well. So can we calculate air gap flux then? Right. What is the expression of air gap flux? If you know all these reluctance, permanent magnet permeance, as well as this leakage coefficient is also mentioned here, right? So this expression is kind of derived as phi v is equal to psi r into this leakage factor divided by 1 plus permeance into reluctance into leakage factor.
Yeah.
This is derived from the current division rule. If you apply similar rule on flux in the magnetic circuit, you will be able to derive this expression. Okay. So we are given leakage factor as 0.95. Permeance of magnet we have calculated as 1.17 into 10⁻⁻⁷. Reluctance we also calculated as 795,774. If leakage factor is 0.95, what is the value of phi r here? Phi r I don't think is mentioned in the problem directly. You have to calculate. Phi r is the flux corresponding to the remnant flux density,
Minute extensity.
and area of the magnet is provided. So can
So
we
B
calculate
by
phi r? Yeah,
B into
phi
A.
b into a. Yes, phi is equal to b into a. So phi r is equal to br into a. Br is 1.1 Tesla and area is 620 Tesla into 625 mm square. How much the value of phi r will be?
6.875 into 10 power minus 4 Webers. This
875 into 10 power minus 4.
Webers.
It is correct. Now we will plug in this value here.
Okay, sir.
It's this value.
Sir, 5.997 into 10 power minus 4.
5.9 minus
4
yeah, it's correct.
Webers.
Yeah. So I hope Chitu, you are also getting the same value.
Yes, sir.
Okay. Yeah. So now we are left with two final problems. Now, we have to calculate permeance coefficient here.
Sir, after the decimal point, there are some changes. Is that okay?
Yeah, that's fine. Some calculation may vary. There are ranges also provided in the answer, so you should not worry about that.
Yes, sir.
So now we have to calculate permeance coefficient of permanent magnet. Certain conditions. So those conditions are given. The magnet height is equal to 6 mm. Air gap length is equal to 0.6 mm. And flux concentration factor is equal to 0.85. Now we have to calculate permeance coefficient. What is the expression of permeance coefficient? Ep
Equal to mu naught into mu r into L by A.
mu naught mu L by A. And yeah, so the area we are not given with, so that equation would not be much helpful. And the equation in terms of flux concentration factor, if you try to recall, which is Ln divided by G into C5.
C5. Yes.
Okay.
Yeah.
So Lm is magnet height, which is 6 mm. Air gap is 0.6 mm. C5 is given as
0.85.
So this will be permeance coefficient.
$11.764, sir.
11.76.
764.
Okay, so now moving on to the last problem of the session. So here it is mentioned that we have 12 slot, four pole, motor with air gap diameter, 51 mm, a stack length as 50 mm, air gap length as 1 mm, quarter coefficient 1.0086, magnet length is 5.5 mm, recoil permeability is 1.1 test, 1.1. Uh, windings Winding is done as such that it has four full pitch square. Winding has four full pitch. Okay. Now, all in series, all of them are series, which means that parallel path is equal to 1. And each winding has 12 turns. We have to calculate air gap self-inductance. Okay. I hope the question is clear to you. Any doubt regarding question?
Sir,
Yes.
what is Carter's coefficient?
Okay, so our Carter's coefficient is, let's suppose we have two cores, okay, and in between there is air gap. So flux from the first core is coming and they are linking to the second core by air gap, okay, but there will be some leakage, isn't it?
Yes, sir.
This leakage is also considered in effective air gap, and that is known as Carter's coefficient. So this, let us suppose this air gap is 0.5, but effective air gap will be higher than 0.5 because of this leakage, because some leakage is happening here. We call it generally fringing flux. So because of fringing flux, the effective air gap is larger than the physical air gap, and that's where Carter coefficient comes into the picture. Okay.
Yes, sir. Understood, sir.
So now here we have to calculate this inductance, air gap self inductance, and to calculate it, first we'll have to let me know the expression of air gap self inductance. So this expression is like flux into number of turns per phase divided by current. Basically, you could also break it as phi is equal to Li. Okay, n phi is equal to Li. You can write it as n phi is equal to L. Okay. Now, this is also further broken into the expression as pi by 4 mu naught turn per phase square into L stack into D, okay, divided by P square into effective air gap, G. So this is the expression derived in the lecture. If you want to see the derivation, you could go through the lecture. Okay. Now here G double dash effective air gap has also some definition, which is multiplied with Carter coefficient into air gap plus Lm divided by mu required. Lm is magnet length divided by this mu required is provided 1.1. So first let us calculate V double dash. So Carter coefficient is 1.0086 into air gap is 1 mm. Lm is also provided And 5.5 and mu square is 1.1. So 5 plus 1.0086, so it will be 6.0086. So you can see from here also, physical air gap was 1 mm, but effective air gap became 6.0086 mm because of the high leakage of the magnetic surface. Okay, now we can plug in this value of G double dash here. So we can calculate LJ is equal to pi by 4. Mu naught is 4 pi into 10 to the minus 7. Transfer phase. How much will be transfer phase? This
Each one
winding
is
did
12
not,
turns. 12 turns.
yeah, 12 turns. Each winding had 12 turns. So how much will be transfer phase? So each winding has 12 turns. 12 will be there. There are 4 full pitch coils. Okay, so total 12 into 4 because total 4 full pitch coils divided by number of parallel paths. So, so let me also write it in generic form. So turns into number of coils divided by parallel path. Okay. So now transport phase will be 48, isn't it?
So, 58.
So I'll plug in this 48 square. A stack length and diameter is given. A stack length is 50, diameter is 51. Okay, so 50 into 51, 10 to the power minus 6. I'm considering both simultaneously. Okay, now
Fine.
P square. So what is the P square? In this expression, what is the P square?
Poles.
Pole pairs. Actually, here it is 4 pairs. So there are 4 poles, so 2 pole pairs
2 per pair. 2 into
into effective,
6.86.
yes, 6.00. Okay, so now I hope you can calculate this value.
Yes. Two point four one two into 10 power minus
2.41 into 10 raised to power minus 2.
Minus 4.
4 minus 4.
Minus 4.
Minus 4. Okay. The answer has, I think the correct answer is 0.241 Henry. But still, let us see where we committed any mistake. I think it is 2.21. Okay. So values we have put all as correct. I don't know why answer, and answer is also very close. Like,
Sir, G double dash in the M 6.0086 into 10 power minus 3 you given,
yeah,
sir.
it is correct. It is correct here. Uh, then maybe answer then may be wrong, but just check once on your own after the session. Okay.
Okay.
Value is correct. Only the 100 and 1000 factors are coming somewhere. But I hope your calculation might be correct. And according to your calculation, you are getting 0.241 millihenry. But in answer, it is given as Henry. So some 10 to the power minus 3, either in the solution manual they have provided wrong, or in answer range, or there
Yeah.
might be some calculation error from your side. So just please re-verify it after this session. Okay.
Okay, sir.
Okay, sir.
Yeah. So this is all about this week's assignment. Any final doubt before we can wind up the session?
Sir,
Yeah.
in the last week, same problem solving session, we have used 2 pi n by 16, no, sir?
Sorry. I couldn't get you. Your voice was breaking. So could you please repeat?
Let me check my internet.
Sorry, I think you are muted. I couldn't hear you.
Sir, could you hear me now?
Still your voice is breaking.
Uh,
But you try once more. Complete your sentence once. Let me catch it.
Sir, could you hear me now?
Yeah. Now your voice is perfect. Yeah, go ahead.
In the last week assignment, we have used 2 pi n by 16, no, sir, for angular velocity.
For angular velocity, we have used 2 pi. Omega is equal to 2 pi n by 60. Yeah,
N
n
by
is
60.
RPM. Yeah.
So, why don't we use 2 pi f there?
Okay, 2 pi f. So see what happens. Uh, 2 pi f is very specific for certain pole number. So let us see what happens. If we plug in here n is equal to 120 f by p. So omega will be 2 pi by 60 into 120 f by p. So now here 2 pi f into 2 by p. Okay. So this factor 2 by p is attached. Why? Because omega is nothing but electrical term. It is electrical frequency. And n is here RPM. And when does mechanical and electrical speed becomes equal? So if you see carefully, this is nothing but a relationship between mechanical and electrical, speed, or what to say, a relationship between mechanical degree and electrical degree. If you recall from undergrad, there will be a term of 2 by p, right? So
Yes,
uh,
sir.
electrical degree is equal to mechanical degree into p by 2. It used to happen, right? So this p by 2 factor is associated with this speed term. And if you ignore this, it means you are considering mechanical degree equal to electrical degree. That's why you have to consider this 2 pi n by 60. Why 2 pi n by 60? Because it is very straightforward. You need not require to remember this Q by T term. Otherwise, if you are comfortable with this terminology, then you can also use it. Okay. So this is what the relationship between electrical and mechanical that appears in the electrical frequency of the system.
Yes, sir.
Okay. I hope that clears. Any other doubt?
No, sir.
Okay. If not, then we can wind up the session. Thank you very much for joining. Okay. Have a nice day.
Thank you, sir. Thank you so much.
Thank you.
Thank you,
Bye.
sir.
Thank you. Bye.